we're going to start today our transition to assembly programming, okay? And in order to kind of both motivate, but also kind of talk about the details of how this is going to work, um, we need to look at basically a little bit more in detail as to the hardware on the Raspberry Pi, specifically the processor, because when we're programming, that's essentially what we're talking to, right? Is the processor. Most of the things are interacting with the processor when we're doing, adding numbers and moving data around and so on. We're also interfacing with memory and then possibly also some sort of devices. For example, when we print something to the screen, right, we're interfacing with the video chip, although the C library and the operating system handle a lot of that for us, so we don't actually have to program it. We just say, hey, put this on the screen, and then bam, it magically appears. Okay, so the Raspberry Pi 4, okay, uses a Broadcom BCM 2711 system on chip. Okay, so what the system on chip means is the chip in the, on the board, okay, this thing has both the processor and the RAM all together inside one actual chip. Okay, so it's not the case like in, say, a desktop computer where your processor is one thing and your RAM sticks are external to that. Okay, for laptop or low power embedded applications, it makes sense to kind of unify things and put them all on one chip if you can. It reduces space, it reduces power consumption. You can also speed things up if you do it right. Apple, for example, has also started to switch to the system on chip model, even with their computers. Okay, so the phone chip, in phones and iPads and stuff, those have been system on chips for quite some time. But the newest sort of the M1 and M2 generation of Apple stuff is also using the system on chip design to, amongst other things, it really you can get some real speed benefits from it. Yeah. And it'll be interesting to see to what extent the rest of the PC industry does that. Intel and AMD don't look like they're going full on system on chip, but they've got to compete with Apple, and so it'll be interesting to see how that happens. So anyway, okay, so we'll talk more about the system on chip parts, but in particular, we want to look at the processor that's in it. So it's a 64-bit quad-core ARM Cortex-A72 processor. Okay, so that's what we want to look at, the details for this thing. Okay, so let's kind of read some of the data stuff here. Okay, pipeline processor with deeply out of order speculative three-way superscalar execution pipeline. We'll talk about all that later. Okay, DSP, don't need to worry about that. But then SIMD and this neon thing, extensions are mandatory per core. Those basically are accelerated floating point instructions that allow you to do so SIMD stands for single instruction, multiple data. It's really handy if you're doing like matrix kind of computations or something that you would do in either video or audio or signal processing. Okay, virtualization, the thumb2 instruction set. We'll talk about that later. Okay, but in particular, the instruction set that it implements, okay, is ARM v8A. Okay, so let's look at ARM v8A. Okay, so the history of ARM, it originally was a British company. Well, it still kind of is. Okay, and the history of ARM as a company was, if we go back into the, I guess it was the 80s, lots of different companies were trying to bring out affordable microcomputers to the market. And so who were the big players at this time in the early 80s? You had the Commodore Computer Corporation, or Commodore Business Machines. Okay. You had Apple with the Apple II. You had Tandy Radio Shack. So how many of you guys remember ever going to a Radio Shack? Yeah. Okay. Nowadays, what do you go to a Radio Shack for? Well, they're kind of also out of business, but what did you go to Radio Shack for back in the day? Right. Batteries. What else? Cords. Yeah, okay. But Radio Shack used to be a really awesome store. Okay. Um, so for example, when I was a kid, if I was working on like an electronics project and I needed like a particular kind of electronic part, like, oh, I need some resistors or whatever. Well, this is before Amazon where I could just click and it showed up 2 days later. So I'd drive down to Radio Shack and be like, yeah, I need this, this, and this. And they'd go on the back and rummage around and see what they had. And off I went. It was great. They got their start, obviously, the name implies, Radio Shack, right? With radios back in the day, before people had televisions, even. You would listen to things on the radio instead of watching them on TV, but also people that were really into like ham radio or CB radio or things like that. You could go and they sold all that stuff and all the parts to repair it and whatever. Okay, so IBM gets into the game with the PC, um, and those aren't the only companies. There was another one in England. The Sinclair ZX Spectrum was one of these machines. So lots of competition for microcomputers, and the BBC, the British Broadcasting Corporation, gets in on the game to develop one that which ended up being called the BBC Micro. Okay, and then uh, it used a processor similar to a number of these other machines from the 80s. And when they wanted to build sort of a successor to it, they kind of ran into a problem because the processors that were available on the market were either too expensive or not powerful enough. And so what they essentially did was this other group called Acorn um, designed its own processor, and that ended up in one of the subsequent BBC computers. Okay, the Acorn Archimedes, it was called, and then it kind of went from there. And early ARM stuff got used for um, in the embedded market. It became pretty popular in the smartphone market. Apple, notably, but they're not the only ones. Qualcomm uses ARM stuff, etc. And then it kind of, has gone from there. Okay. Um, but the part about the ARM v8 instruction set that we need to think about are uh, this stuff here. Okay. So, um, registers. So think back to, has anybody ever seen or used, I doubt you've ever used one, either a mechanical calculator or an electromechanical calculator, or even a really old timey cash register? No? Okay. Well, anyway, the display on that was called a register, right? In the same way that, like in bookkeeping or something, you keep track of registers of accounts. Um, and so with CPUs, internal to them are a bunch of little memory cells, essentially called registers, where data that you're currently processing resides. So if I want to, for example, add two numbers, okay, on this architecture, what I have to do is I have to load one of the numbers into a register, load the other number into a different register, add the answers or add the two numbers, and then the result I put into a register. Okay. Um, and if I want to then store that into memory, that's a separate instruction. So there's sort of two categories of instructions: things that move data from memory to a register or back. Okay, so load and store. And then there's things that operate internally only on registers, like doing arithmetic, adding, and so on. Okay, good? All right, so how many of these things do you have? Well, for the integer stuff, we have 31. It's really 32, but there's one of them that's sort of reserved for special purposes. So we have 31 of these things. They each are 64-bit wide. Now, that may not seem like a whole lot of these things, okay, but it's actually a glorious number of them, okay? So for comparison's sake, let's look at a processor from the early 80s, well, late 70s, but it was used in the early 80s. How many, the 6502, okay, so this was the computer or the processor in the 8-bit Nintendo and a bunch of those other kind of machines from that era. It has basically 3 registers, right? So it was very register limited and therefore depended a lot more on memory, okay? And the so the fact that we have 31 of these things is actually pretty glorious, okay? Okay, great. So let's go back to R1 here. Oops, back one more. Okay, so the fact that we've got these registers, that we have basically 31 of them, is very nice. Now, as we're going to see, there are certain conventions as to what you're allowed to put into what registers when, and so on. Okay, so there's a lot of details there, but yeah, okay. So that's just kind of the quick overview of the processor that we're working with. Now, because we're working with an ARM processor, that means we're learning a particular instruction set for a particular processor, okay? Intel architecture is different, and the instruction set is different. And there are certain nice things about Intel's instruction set. There are certain irritating things about Intel's instruction set. But it's a different processor, different instruction set, okay? So, and I'll demonstrate what I mean here in a second. So let me open up VS Code. Okay, and let me go back to, well, let's do the very first program we wrote, the Hello World. Okay, and let me close all of this stuff. Okay, so the very first program we wrote, right, was this silly Hello World routine. Okay, nothing particularly fancy, and oops, I'll fix all that other stuff later. Okay, and we executed it, and it printed hello world, and all life was good, right? Okay, so I did this before, and I'll show you the commands for how to do this later, but if we look at the assembly for this, I've made 2 versions of the assembly. Okay, so when you give a C program to a compiler, what it's going to do is process that source code and spit out assembly for your target architecture. Then another program called an assembler takes that and actually turns it into all the ones and zeros and stuff. Okay, so the actual instructions, the actual machine code. And then there's a third process that happens called linking, where it links to things that are in like the C standard library. So for example, when we use printing or get string or scanf or something like that, what I'm really doing is just saying, hey, go use this thing over here. Okay, so that's the linking process. Now, when you type GCC with a piece of source code and tell it what to output, it does all three of those steps all in one swell foop. So it doesn't appear to you that it's three separate processes that are going on, but there really are. Okay, so we're going to peel back the layers on those processes. Okay, so here, if I look down at my main routine, okay, I can see there's a bunch of these instructions, and we'll talk about what these things mean. So, like for example, the first sort of real instruction here is STP X29 X30 SP -16 and an exclamation mark. Okay, what the hell does that mean? We'll worry about that later. But this is the first instruction for the program if we look at it in ARM assembly. If we look at it in Intel assembly, the first instruction is push Q %RBP, okay, whatever that is. Okay, so even though this is the same C code, when I compile it to assembly, now I have to worry about the actual hardware that I'm executing this thing on, right? So C is high level in the sense that, does it matter, like if I'm writing C code, does it matter what kind of computer I'm doing it on? No, okay. But then, and if I compile it and run it, it'll run basically, from my perspective, the same on any computer. Okay, so in that sense, it's high level. It's abstracted away from the hardware. Okay? In another sense, it's not abstracted away from the hardware because, for example, we have to worry about memory, right? And in particular, things like pointers and whatever. So that's sort of lower level in the fact that we're thinking about a computer as being a thing that has memory. But do I have to know exactly how the memory is laid out on the machine or any of those sorts of details? No. Okay, so it's um, abstracted a little bit away from the hardware. Assembly, we're going one layer down from that. Okay, where not only are we worrying about the hardware in terms of memory and stuff, but we're worrying about, well, which processor or which type of processor is actually executing all of these instructions. Okay, good. Okay, so let me do one other thing down here, and don't worry about what these commands are right now. I'll type them out later for you guys. But oh, is it? What is it? Ah, crap. Okay, hang on. I thought it was -A. Huh? That should be the output file. Oh, it's just an A. Sorry. Oh, okay. Hold on. 1 second. No, it should be -A, unless they've changed it on me. Okay, they've changed the command on me. Maybe we have to do the debugging. Okay, well, then they've changed the command on me, so I will figure that out later. Um, so, okay, whatever, we'll deal with that later. So, what I was wanting to do is basically show you how this stuff gets encoded into the actual instructions, and I can do it another way. Um, okay, yeah, we can do it this way. Okay, so let me open up a big terminal just for sake of clarity. All right, so we were in programming and we were in hello world, and let's look at, we'll do an object dump, and I want dash B of hello. Okay, why is that not, or sorry, not dash B, dash D. Okay, here we go. This is a different way of getting at what I was doing a minute ago. Okay, so if we look at all of this, right, um, there's a bunch of um, things going on here, but in particular, uh, so what we have are looking at this beginning part, we have the instruction. This stuff to the right of the instruction are going to be any operands that the instruction needs. So, for example, if I want to add two numbers, and the two numbers are already in registers, I have to say I want to add, well, which register am I adding to which register, and where am I going to put the answer, right? I need to specify all of those things, okay? So those things are the operands. The instruction in that case would still just be to add or whatever, okay? So here, I have um, the instruction, the operands, okay, and then this bit over here, that 32-bit number, okay, is the actual instruction encoded in, well, displayed here in hex, but the actual instruction, okay? What do you notice about the instructions just kind of looking down the line, right? You're not going to notice any particular pattern of the numbers or anything, but what do you notice there? Anything jump out as sort of interesting? Okay, maybe not yet. Okay, but we do the following. Oh, I want to do, okay. So what I just did was I made a second executable version of this, but I had the GCC generate an Intel executable rather than an ARM executable. Now, if I try to run it, oops, not that one. Okay, it's not going to let me. Why? Why won't it run? Yeah, it's a binary for the wrong kind of processor, right? I'm trying to do and read and execute an Intel piece of Intel code on an ARM processor. There are ways you can actually do that. You sort of emulate an Intel thing. But if I do the object dump like I did a minute ago, okay, and then let me do hello Intel instead. Oh, right. There is that. Let's see. There is a way to fix that. Okay, and so I want, let's do, see, it's dash D dash Intel x86-64 dash B binary dash M6 okay, and we just start pulling off. Okay, well, whatever. It would have been nice if the listing file command didn't change. I could have sworn that was dash A. Okay, anyway, the what I wanted to kind of show you was, so Intel, well, actually, we can just do it this way. Well, that's not really going to be useful. Okay, so let me kind of back up a moment. Let me go back to the object dump that I did for the this one. What do you notice about the instructions? The length of the actual encoded part. How long are they? So all of, huh? It's all how many bits? 32. Okay, so each pair, there are 8 pairs of hex characters. Each pair is an 8-bit thing, and there's 4 pairs, so that's therefore 32 bits. Okay, they're all 32 bits. Isn't that nice? That every single instruction is 32 bits? How is it on Intel? They're not all the same, okay? So this is sort of one of the legacies of the Intel architecture, right? The x86 architecture goes back to the 70s, right? And in the 1970s, how big were the processors or how big were the registers? Well, they either held 8 or 16 bits. It kind of depended at exactly what time you were talking. Okay, but the Intel, like I said, the x86 architecture, one of its greatest strengths is the fact that you can still run code on it that was written, like you could still run binaries that were written in the 1980s on your modern Intel machine. That's kind of crazy, right? The other thing is that architectures of back then, so think into the 1980s, like how much memory would have been in a computer? I mean, how much memory is there now in a modern computer that you go buy today? How much RAM would there be? Yeah, 8 or 16 gigabytes sort of minimum. I mean, heck, the phones nowadays, like the iPhone 14s that they just announced last week or whatever, have like 6 gigabytes of RAM in them for a phone, right? Now, granted, it's not just a phone, right? And you can play games and stuff on it too. But um, the right, so we're talking gigabytes worth of memory. That's a lot of memory, yes. Okay, how much memory were there on computers from back in the day? So in the 80s, how much were, like, what kind of order were we talking? We were talking kilobytes. Yeah, so like the Commodore 64, for example, that I love, right? It was called that because how much RAM was in it? 64 kilobytes. Okay, that's not a whole lot. Early IBM PCs um, or early PCs had, you know, maybe 640K. So you guys ever heard that Bill Gates thing, right? 640K ought to be enough for anybody. He's referring to, that if you can't do it with 640K of RAM, then you shouldn't be doing it. And then now look at where computers have gone. It's kind of gotten ridiculous. Okay, so early machines back then were very RAM limited. Okay, so architectures of the day tended to try to squeeze as much into an instruction set as they could, and the best way you could do that was to have variable length instructions. If it was a really short instruction to, like, for example, there's an instruction to not do anything. It's called a no op, which just means sit there for a cycle and don't do anything. It's kind of a silly instruction when you think about it, but it's useful in certain contexts. That, should it need a really long encoding? No, it's just there's nothing to do, right? But other instructions like doing addition might need longer encodings. Okay, so the Intel architecture and others of the day had variable length encoding, and what that meant is that they were very memory efficient in terms of storing stuff. A fixed length encoding like ARM, where every single instruction takes 32 bits, is not particularly memory efficient, but does that matter anymore? In a sense, no, because our computers have so much memory in them that, like, that's not the problem, right? The problem is not how big your instructions are for your programs. What is it that fills up your computer, right? What is it that fills up your computer's memory? It's not programs anymore. I mean, unless you're running something really horrible like Photoshop or After Effects or whatever. But what mostly is the stuff that takes up all that memory would be movies and sound files and, websites and media that takes up a lot of space, not the actual programs. Okay, so um, anyway, every instruction on ARM is exactly 32 bits wide, and that's very nice because it means that when you're reading these things out of memory, you don't have to think about, well, how long is this instruction going to be? You just pull in 32 bits, decode it, and do it. Okay. Um, okay. So let's look at how this stuff actually gets executed. Um, all right. So um, let me do one thing here. Okay. So I'm going to take, um, we looked at, so I've got the assembly here, the .s. Okay. Now this is machine produced assembly, meaning that I told the compiler, hey, bro, can you output assembly instead of an executable file? I did that with the flag on the instruction, okay? There's a bunch of stuff up here. We don't really have to worry about what all it means right now, but let's look at kind of the meat of the program, which is something about here, um, uh, there's some storing, there's some moving, there's something going on here. We've got this branching thing, BL, that stands for branch and link. We're moving 0 to a register. We're doing something, and then ret. This is kind of like return in C, right? This basically tells it to return from this subroutine to the thing that called us, and which in our case is the operating system, okay? And then there's a bunch of this data stuff down here that's just, there. Okay. All right. So let me actually here execute. What I'm going to do is I'm going to GCC. I'm going to go ahead and add in the debugging and the static stuff. And I'm going to do hello.c, but I'm going to output this to hello2.s. Okay, then I'm going to, so the dash, oh, I'm sorry, and I forgot the -s flag. There we go, okay. So the hello2.s, okay, let me remove that because I need to, there we go, okay, messed it up. Okay, so this hello2.s, let's open that up and look at it. Okay, it basically looks the same thing as what we had. There's maybe a few other things going on there, but because I had it put in some debugging information. Okay, but I've got all of the actual instructions there. Okay. Now, I need to, how do I turn this into something I can actually run? I do that with a new command called as for assemble, okay? And I want to assemble what file? I want to do hello.2.s, and I want to output this to hello2 with no extension, okay? Or I'm sorry, not hello2 with no extension, .o. Okay, so what that has done is produced a new file, an object file, okay, which is almost executable, but not quite ready for that. It needs to be linked to things like puts and whatever, okay? And in order to do that, I can just use GCC again, okay? So I'm going to do GCC-G-static for reasons that'll become clear later. And then this time I'm using hello.o, not hello.c, and or sorry, not hello.o, hello2.o, and I'm going to output to the executable hello2. And then if I run hello2, still does the same thing, okay? But I've basically manually done all three of the steps of compiling. Compile to assembly, assemble to object code, link object code to make it executable. Okay, and now if I run GDB with this, okay, oh, right, hang on, that's not what I wanted to do. Let me take, yeah, okay. So this is not going to do quite what I want because we started with C program rather than actual assembly. Okay. So let me make a new directory here and let's actually start handwriting this stuff. Okay. So I'm going to make a new folder. Okay. And I'm going to call this hello2. And then let's handwrite some assembly. All right. So let's close all of that. Okay. Here's my convention for naming assembly files. There are two different extensions that are logical to use. .s, okay, is kind of a historically relevant one, and .asm is the other, okay? And I deliberately use both, but I use them in different contexts. So if I am handwriting assembly that's produced by me, I use .asm. If I am machine producing assembly using the compiler, I use .s. Okay, so machine produced .s, human produced .asm. Okay, what's the benefit of having that distinction? Yeah, you know which one's which. Okay, and there are times when you need both of them, and this just keeps it organized. Okay, so okay, so an assembly program needs to have certain sections, okay, and these sections are basically different things are going to go in them. Most of the assembly file is going to be below the .text part, okay? Our functions will go there, all the actual instructions will go there, so most of that stuff is in the quote text section. But for some programs, like, we need some data, okay, that data could be something like a string that says hello world or whatever, okay? So in fact, let me go ahead and define that. So I'll call hello string, okay, is ASCIZ, okay, is the, oh, and I need a colon right here. Okay, so I have just defined that there is a string called hello str, and it is hello world with a carriage return at the end. Okay, now this ASCIZ, that basically, I need to specify, well, what kind of data am I putting in here? A string, but a string encoded in how? How do we encode strings? In ASCII. Okay, so what's the Z stand for? Any guesses? It stands for 0. Okay, how do I know that I've hit the end of a string? There's a null terminator at the end of it. So what the Z means is that it's a null terminated string, which is basically the way we always do it, right? So, yeah, okay. So does that make sense? Yes. Hmm? Oh, that's just the name of it, right? So the string's got to have a name, right? And um, I just chose hello str as its name. I mean, I could have named it chicken tender for all I care, right? Um, and obviously, pick logical names for this, but this would be like in C, right? When I declare a variable, I need to say what data type is it and what am I going to call the thing? And I just picked hello str for sake of example. Okay. Okay, so good? Yeah. All right. So um, the function here is called main. Okay, and what kind of function is this? It needs to be global, so I have to have this dot global and then main. And then below that, I'm going to put main colon. Okay, that's called a label. And below that, I'll put the actual instructions that go into my program. Okay, make sense? Yeah. Okay, the very first instruction of any ARM program that you guys are going to write should be this. Always. Okay, and I'll explain later, like in maybe a few days, what the heck that actually means. Okay, suffice it to say for now, the idea as to what it means is okay, so you guys know the story of Hansel and Gretel, right? What's the story of Hansel and Gretel? They get eaten. Okay, but what do? They go wandering, trying to escape the forest or find something, right? So what do? Yeah, they leave a trail of breadcrumbs so that they can help find their way back out. Okay. And in the story, something eats the breadcrumbs, and so it's a big disaster, right? But the idea is if I wanted to get from here to, um, you know, the bathroom downstairs and back, and let's just say that it's pitch black and I can't see anything, okay, how could I find my way down there and then ensure that I found my way back? If I can leave some sort of trail, like a string or breadcrumbs or markers, like, X's on the wall or something, like, then I can maybe find my way back by following the breadcrumbs in reverse order. Yeah, that's kind of the idea. That's what this instruction and then the one that we'll put at the very end um, basically do. That instruction says put down a breadcrumb, and then the one at the very end will say pick up a breadcrumb and move on to the next breadcrumb. Okay. Now the details of what the breadcrumbs are doing and stuff like that, and where we're going, so to speak, we'll talk about later. But um, that's essentially the idea. Okay. Uh, so the thing that goes at the end to go with it is this. Okay, and oh, let me change the syntax highlighting to ARM assembly instead of 6502. Okay. Okay, so the very first instruction is this store pair. That's what STP stands for, store pair. Okay, the LDP stands for load pair. And so the shell of basically every main routine you're going to write is this. Put down a breadcrumb at the very beginning, pick up a breadcrumb at the very end, and return. Okay, and so this return basically goes back to the operating system. Says, so as far as the operating system is concerned, our program is a subroutine. Okay, and that program could itself have subroutines, as we've seen with C. Yeah, okay, so that is sort of the shell for everything. Now, what do I want this program to do for my sake of demonstration, my Hello World program? All I want to do is have it print Hello World. Okay. Now in C, how many instructions did it take to do that? What did I type in C if I wanted it to print Hello World? Yeah, I used the put s function for put string. I could have also used printf, but I'll just use puts for right now. It was a single line of code, right? Puts, parentheses, string, parentheses, and then of course a semicolon because it's C. Okay, one single instruction in C. But how many is that actually in an assembly? It's going to be more than one instruction. Okay, and the reason is as follows. So think about, for example, when I used printf. Let's say I used printf to print a number. What did I have to do with printf? I had to give it a format string, like %i, and then I had to also give it the number I wanted it to print. Okay. When I give it a format string or a number I want to print or a string I want to print, what really am I giving it? I'm giving it a pointer, right? I'm saying, okay, I want you to go out into memory and print the thing that's located there, okay? And so I need to do the same thing here. I've got this hello string that I've defined in my data section, and it's someplace out in memory, okay? I don't know where that is. So how would I have gotten its location in C? If I defined a string and I wanted to know where it was, well, actually, I wouldn't have to do that with a string because the string's name is its pointer. But like, let's say an integer. I have an integer that I'm storing in memory. Let me call it, my num equals 5 or int my num equals 5. How do I figure out where 5 was stored out in memory? Yeah, the ampersand operator, right, basically generated for me the location of that thing. It generated a pointer, okay? And then I could store that data, that pointer, or do whatever I wanted with it. Okay, great. Same thing here. I need to know where this string is in memory, okay? If I'm going to call the function puts to put some data on the screen, and I need to tell it, well, what string do I want it to print? Okay, I have to say, I can't give it the string, but what I can give it is the location of that string. Okay, so I need to do something like the ampersand operation from C here. Okay, and the way we're going to do this is I'm going to do LDR x0 equals hello string. Okay, so what that's going to do is it's going to take the address of hello string, whatever it is. It's going to load that address into a register. Okay, and which register is it going into? The very first one, okay? So how many registers do I have total on this machine? 31 basically, okay? It's really 32, but like I said, there's some special purpose ones, okay? And there's a convention as to what order you use these things in. Okay, that convention is partially specified by Linux, but it's also just, like being sane. Um, so which register should you use? Well, let's start with the one at the beginning, okay, which is called X0. Okay, so we'll talk more about this later, but um, the registers on this thing, how big are they? So there's 31 basically of them, but how big is each one? They're 64 bits, okay? And if you are talking about an integer register that's a 64-bit one, its name is X something. Okay, so X0, X1, X2, X3, and so on. Okay, but we also can use just the 32-bit sort of chunk at the beginning of it. Okay, in which case we call it a W register. The W is a subset of the X, and we'll talk about, in math and stuff later. Okay, but the reason, or like to do arithmetic and stuff, that will matter. The reason that I need to put this into an X register is because, well, how big is a memory address on this machine? Okay, when we looked at the memory addresses when we were doing stuff in C, how big were these memory addresses? Yeah, they were 64 bits, right? It took 16 hex characters to write them down. Yes? Okay. So 64-bit address means I need to put the address in a 64-bit register. Hence why it's X. Okay. And why is it X0 as opposed to X7 or whatever? There's a convention about the order that we use these things. Okay, which we'll talk about in glorious detail for the remainder of the semester. Okay, you guys are going to be so sick of this by November, it won't even be funny. Okay, so I need to do that. And then the other thing I need to do is, well, okay, so in C, how did I do this? I said puts, parentheses, and then the string. Okay, or it would have been equivalent if I said puts, parentheses, and then the name of the string to go print, right? Okay, so have I actually told anything to do any printing yet? Nope. Okay, so I need to call the the subroutine called puts. Okay, and I do that with this instruction called BL. That stands for branch and link. It's essentially how I make a subroutine call. And the linking, we'll talk about that more later, that has to do with the breadcrumb situation. Okay, which, like I said, we'll talk more about the breadcrumb stuff later. Okay, so you want to call a subroutine, usually you're going to do a branch and link. Okay. Okay, so is there anything else to do for this particular program other than assemble it and make it run? Like, do I need to write any more code here? The only other piece of code I'm going to do is, what did we put when we were writing this stuff in C? What was the very last instruction of our main routine? Return 0. Okay, so I'm going to move the number 0 into W0. Okay, and I'll talk about that in a moment. And then return. Okay, so return 0 in C really is move W00 and ret in assembly. Okay, so not every C instruction corresponds to a single assembly instruction. Okay, all right, so now we need to assemble and run this dang thing. So let me get into the correct directory. All right, and then I'm going to assemble this. object file. Oops, let's see, warning, end of file, not at end of line, new line inserted. Okay, whatever. Let's see if that does it. Okay, I just needed an extra line, whatever. Okay, great. And then I'm going to link it. And if I run it, it sprints up hello world. Not shocking, that's what it was supposed to do. Yeah. Okay, so let's look at the instructions that I followed here. This first one is that I assembled it. Okay, so assembling takes the .asm file and spits out essentially the machine instructions. Then I have to link it because I've used something external to my program, namely puts, right? That's a routine that I didn't write. It's not defined in my program. I'm just calling a reference to something that is in the C standard library, okay? And so I need to assemble it and I need to link it. Now, I don't have to use GCC to link it, but because we're using stuff from the C standard library, that's the most logical thing to do. And then I've added in the flags here, -G and -static. The G is for debugging symbols, and the static will make the debugging easier. I'm not, like, if I'm just writing a program, I won't necessarily put those flags in. I find them useful for debugging purposes only, really, okay? All right, so now what I want to do is let's look at how this thing actually gets executed on the machine. Okay, and for that, I'm going to use our friend GDB. Okay, so this is maybe a little hard to see because it's at the bottom of the screen, so let me move it up a little bit for you guys. Okay, so what do I have here? I've got now, I'm not going to step through instruction by instruction in C. I'm going to step through instruction by instruction in assembly, okay, the actual machine stuff. Okay, so what's the first instruction that I need to do? Basically, this is to put down the breadcrumb thing, okay? And it has not actually executed it yet. That's the instruction I'm about to execute. If I step one more time, it will execute it and show me the next instruction that's ready to be executed. Okay, so let me blow this back up to the full screen because I need all the space. Okay, so here is what's in all of the registers, all of the integer registers. Okay, and looking at all this, what do you see? There's a whole bunch of gobbledygook, right? And like, for example, what do any of these numbers have anything to do with anything? I don't know, okay? I mean, some of them I do, but as far as we're concerned, that's all gibberish, okay? Now, there are some nice numbers, like, for example, the number 1 happens to be in a register, okay, great. But and then there's all this other stuff going on. So for example, what I'd like you to pay attention to for right this instant is those two registers, okay? So 7FFFFFEFB0, does that like remind us of anything that we've seen before? Kind of looks like some of the memory addresses we've looked at before, okay? And then if let me execute the instruction and look at them again. Now what is it? Yeah, it's different. It's now EFA0, whereas before it was EFB0. Okay, so something has changed about this X29, or I'm sorry, hold on. I think I looked at the wrong one. EFB0. Now it's still a EFB0. What I wanted to do was to look at, okay, let me start this over. Okay, so I'm looking here at EFB0 and so on in memory, and what do I see? A bunch of zeros and some other stuff. But if I step one more time, now what do I see? Yeah, okay. So basically what I've done is this is told, this is the breadcrumb. There it is right there, okay? And like I said, we'll talk more about the breadcrumb situation later. Okay, so let me step one more time. Okay, so what just got executed was the instruction to load X0 with the address of the string I want to print. Okay, so if I look at the registers now, what's in X0? 48A048. Okay, that might as well be random as far as we're concerned, but if I look out at memory, what do I see there? What was the string that I wanted to print? Hello world, right? Do I see that string? Do I see that data here? I do, right? Because what's the capital H? Careful. It's actually the 48, right? It's not in the right. It doesn't look like it's in the right order, but here's the H, here's the E, then the two L's, and then the O, and then a comma, a space, the W, and so on, right? So that number that I put into X0, this 48A048, is the beginning memory address where the string I want to print is located, okay? And I need to put that in X0, that number, so that I can basically hand this to the printing function, puts, and it's going to receive that, go out to memory, and whatever it finds there, dump that to the screen. Yes. What? The instruction here, LDR X0, comma, equal hello string. So the equal here in assembly is kind of like the ampersand in C. Hello string is the name of the thing. Equal hello string is its location in memory. Okay. And then which register am I putting that into? X0. There's a convention, like I said, about the order of these things. Okay. So there's the string in memory. Okay. And I'm about to, the instruction that's about to execute is to basically tell puts to do its thing. Yeah. Okay. It hasn't done it yet, but it's about to. Okay. And there it is. Hello world. It printed. Yay. Okay, and the next instruction that's about to run is this load pair, basically to pick up the breadcrumb. All right, so we'll step there, and then I'm going to put W0, the number 0, into it. So let's look at what's in register 0 right now. F, or 15, right? What is it after I execute the instruction to put 0 in it? I would hope that 0 gets into it, yes? Okay, And then ret, if I step one more time, the program will terminate, and that's the end of it. Okay? Oui ou non? Okay. So, basically, y'all's very first assignment with this is to do this process, okay? And essentially the code will look exactly the same as this, with one exception. What did we do with assignment 0? Instead of hello world, it was, yes, it printed your name, okay? But you guys are going to type this out on your Pi and assemble it, okay? And then the other thing, which is I want you guys to generate listing files. I'm blanking. They've changed the flag for it. I'll look that up and then put the instruction for what to type to get the listing file on Canvas. But essentially what the listing file will look like is it's kind of like a, well, here, it's kind of like this, but it's in a text, like a file that you could open in a text editor or VS Code or something like that, rather than just being a bunch of data in the console. Okay. And, uh, you know, the why I want you guys to generate these things is not important at the moment, but it will be later. And by having you guys get in the habit of doing it now, that'll save us trouble later. Okay. Because later, what we're going to also worry about is actually what this encoding means for certain instructions, not for all of them. There's too many. But for some of them, that in looking carefully at the encoding and reading the 5,000 page manual from ARM can actually elucidate how things are working. You don't like the idea of reading a 5,000 page manual, Patrick? Doesn't sound, well, we're not going to read all 5,000 pages. Huh? Yeah, it is. Well, it's not all non-English. There's a lot of English there too. Yeah. So, okay. All right. So I will post the correct console command for generating the listing file to that assignment in Canvas, and I haven't had coffee yet, so it's probably just that. All right. I guess let's quit a little early, and I'll see you guys on next week.